So let me just provide you with the theorem. The theorem is that a function f from a, b, an open interval a, b to R is uniformly continuous on a, b if and only if it admits a continuous extension to the closed and bounded interval a, b, where we recall that function f from a to b R, the closed bounded interval, is continuous if and only if it is uniformly continuous. Okay. Now, I told you to prove this claim, so I'm not going to prove it today. However, I want you to think about the compactness of this interval. The compactness of this interval means that essentially any open cover can be reduced to a finite subcover. Okay. So somehow the compactness of this interval forces continuity to be equivalent to uniform continuity, because somehow if we want a uniform delta, we can just choose we can take a finite epsilon net of our interval and then look at the delta, the modulus of continuity on each of those balls and take the minimum over the finite epsilon net, and we'll get a uniform modulus of continuity on the whole interval. So again, I will prove this more rigorously at a later time, but I want you to think about it yourself. Now, this is kind of a bombshell theorem, and it says that, and I told my student, I was like, this is so powerful. And it says that a function, a continuous function, let me state the theorem correctly before I say it's powerful. A continuous function from an open interval a, b to R is uniformly continuous if and only if it admits a continuous extension to the closed interval a, b. And so this theorem answers the question that a continuous function is a continuous function something that you can draw on a piece of paper without picking up your pencil? And the answer is no, that's a uniformly continuous function. Because every time you draw a line on a piece of paper, you are inherently drawing it on a closed interval, a to b, okay? So you're drawing this on a closed interval, and so naturally, this function must be uniformly continuous. And yeah, so for you to even put your pencil down and then pick your pencil up when you're done drawing the function means that there's some sort of continuous extension. And so somehow this theorem is telling us that the familiar notion of continuity that we're used to of drawing a line on a piece of paper is really a notion of uniform continuity. Okay? It's somehow stronger than just continuity. Now, why is this theorem so powerful? Well, let me give you an example. So let's look at the function x times sine 1 over x on the open interval 0, 1. Okay, well, we know that the limit as x approaches 0, the only question, first of all, the only question about this function having a continuous extension to the closed interval 0, 1 is whether or not its limit exists at 0, okay? So if we look at the limit as x goes to 0 of x sine 1 over x, then this is just, by the squeeze theorem, this is less than or equal to the limit of x as x approaches 0, and less than or equal to the limit as x approaches 0 of negative x, absolute value. And so here, this gets squeezed between 0. And so we identified that this limit exists and is equal to 0. And so it does have a continuous extension. The continuous extension is simply to be given by setting the function equal to 0 when x equals 0, and then sine of 1 when x equals 1. Okay? And so yes, this is, yes, x sine of 1 over x is uniformly continuous on 0, 1. Okay? So this example, this would normally be very hard to do algebraically or using the epsilon delta definition, but it becomes easy when you invoke this heavy-duty theorem. Now, okay, let me just note that f has a continuous extension if and only if limit as x approaches a from the left of f of x and limit as x approaches b from the right of f of x are well defined. Okay, so basically the idea is if I have a continuous function on an open interval AB, then to check that it's uniformly continuous on that open interval, I only need to investigate the limit as x approaches a from the left of f of x, and I need to look at the limit as x approaches b from the, and of course I wrote these incorrectly. Life is rough. Life is rough. Okay. Anyways, so yeah, so I'm approaching a from the right side because, I'm approaching a from this side, and then I'm approaching b from the left side. So I want to put a minus sign there. Okay. And so if these two limits exist and are well defined, then they're the values of our continuous extension at a and at b. I'm going to define the continuous extension at a to be exactly the value of this limit, the continuous extension at b to be exactly the value of this limit. The function will be continuous on this closed bounded interval AB by definition, since a function is continuous if and only if limit as x approaches a of f of x equals f of a for all points a. So basically it'll be continuous by definition, and then by this theorem it'll automatically be uniformly continuous, since it's continuous on a closed bounded interval. So this theorem is somewhat of a direct corollary of this previous statement. So I'm not going to prove this one either because it's coming directly from the theorem that I want you to prove. Okay. But yeah, just recognize, even without knowing the proof of this, or maybe you do know the proof of this, but this theorem allows you to solve some seriously difficult problems very, very quickly. For example, the x sine 1 over x was just instantly solved with this theorem, whereas it would have taken a lot more time if we didn't have this theorem in our back pocket.